all been waiting for.
Probably in our the field that we're yeah, probably did.
After 10 years of
Oh, yeah.
Yeah, there's a training for non-toxic signal officer.
I was until I ate figs.
What happened? This is all both the true chapters?
Yeah. Be too small.
I'm good, man. I'm still young, my eyes work. The sea monster just ambushed me.
someone like mentioned before, there.
Because no, because the
our 245 rating do some of the similar stuff, but the 245 rating supports like 32 megabits per second. And then some of the data you put out is limited by like their rates, the 245 rate will be limited by data, certain kinds of data that are not limited by and that's where like the guys here also
Other than midweek days, so we got tomorrow. We're just hanging out doing homework and that's it tomorrow?
I don't think so.
Not bad enough.
I thought that's what I thought.
No one really talked about it.
We're not at all. I don't know, but it's in the afternoon anyway. So.
I remember for extra saying it was impressive. Maybe better figure that shit out. You haven't figured out how to get into places once and you're not suitably also your homework? Yeah. I'm kind of worried. Why are there not cheat sheets or chapters 10 and 11?
No, some very curious things showed up. It showed up.
They're easy. Graphs.
This is the game
Dude, all I want is fairly cheap.
Wow.
It's ridiculous. It's not really they were all shit bags. There was more of them that could have got one filled the APFT, the other two, one was just like openly hostile to everyone, and then the other one was kind of useful as your mental. Like, we worked on group projects, and this guy was like taking the cars, and like he told like friends, he told some Greek writer, hey, we're going to go to Dublin. Okay. So he, no, then he goes and posts on his Facebook of him drag racing some guy, like while he's supposed to get a dental appointment. I'm like, really?
Okay. I hope that's a lot of lines. I hope so. In the triangle.
Oh, yeah.
Big A's. Down.
All right, so the final topic today, which we'll end the day with, is solving triangles. To solve a triangle, what that means is find the length of all its sides and find all its angles. And usually what you get is you get partial information, enough to solve the triangle. So you might get maybe two angles and the side connecting them. And that uniquely determines the rest of the other quantities. So you're given typically 3 quantities. You're asked for 6 quantities. You're given 3, and you have to find the other 3. That's solving a triangle. And the way we're going to do it is you're going to use 2 general laws, the law of sines and law of cosines. So the law of sines says as follows. Well, first of all, standard notation for a triangle, the angles we'll call A, B, and C, going around the triangle. The opposite side, capital A, capital B, capital C. The sides opposite the angle are listed as lowercase. So the side opposite angle A has length little a. Side opposite angle B is little b, and the side opposite angle C is little c. Okay, that's the standard notation. So in this setup, the law of sine says the following. The lengths of the sides are proportional to the sines of their opposite angles. So A over sine A is equal to B over sine B is equal to C over sine C. All these ratios are the same around the triangle. You can flip all of these and say sine A over A is equal to sine B over B is equal to sine C over C. That's the law of sines. So this allows you to get some things in terms of other things. So note for the right triangle, the law is trivial. So for example, if the right angle is at C, and so C is the hypotenuse, little c is the hypotenuse, then C being 90, the sine of 90 degrees is 1. So that's 1. So I have C over 1. And then the other ones just say, for example, sine A of big A over little a is 1 over C. Multiply through by A, and I get the sine of A is just A over C. Well, this is just the opposite over the hypotenuse. And sine of B is B over C. That's the opposite of B over the hypotenuse. So if C is 90, we've already seen this before. The problem is now this is a general triangle, and none of these angles may be 90 degrees. Okay. So remember back in geometry, you may have been said, okay, there are these rules that say if you know, for example, an angle side or an angle side angle, that determines a triangle. So AAS means you go around the triangle, say, in one direction or the other, take an angle, take another angle, and then take the next side you get. So AAS, I might give you A, capital A, angle B, and side little a. That would be AAS. ASA is angle side angle. Here you take an angle, and then the side incident to it, and then the angle on the other side. That's ASA. Okay. Or you could do SSA or ASS, which is angle, side, and then side, like that, for example. So use this law whenever you have one of these. So let's do an example, an AAS example. You're given A is 60 degrees, B is 45, and little a is 2. 2 inches, say. Find the remaining angle and sides. All right, so we can use law of sines, but there's another law to use that's also useful, and that is the sum of all the angles is equal to 180 degrees, equal to pi. So this is true in any triangle. What this means is, once you have 2 angles, you get the third one essentially for free. So here we've got 2 angles, 60 and 45, so that immediately tells you that C has to be what? 75. 75 degrees. Don't forget to put the circle there. So, now we've got all 3 angles, so we, in principle, know what their sines are. And we know what at least one of the sides is. A is 2. So from these 2 equations, so like from this first equation, we can immediately get B because we know all the other 3 quantities. And from the second equation, we can get C because we know the other 3 quantities. So for the first equation, sine B over sine B is equal to A over sine A. So B is A sine B over sine A. Plug all that in. Now these happen to be special angles just by luck. So instead of going to the calculator, let's just plug in the exact quantities. We know what they are. Root 2 over 2, root 3 over 2. That simplifies 2 root 2 over 3, or 2 root 6 divided by 3. So that's B. That's actually an exact answer for B. Generally, these won't be exact because they won't be special angles, and you'll have to, and an approximate answer will suffice. So let's find C using the other equation. So C is A sine C over sine A. That's sine of 75 degrees over sine of 60. Well, we can get an exact answer for sine of 75 because it's the sum of two special angles. Okay, so to make a long story short, we get that. Simplify, we get that. Probably you should multiply it through by root 3, but we're not going to do that, so we're just going to leave it like that. Okay. Oh, I guess we are going to do that. Just the animation is not being nice. Okay. All right. That's good. Okay. So have we found everything now? We found, we haven't, so we found C. C was 75. We found B, and we found A. And we found little c. So yeah, that's everything. So we solved the triangle. Good. So let's do the SSA case. I see. So SSA case, let's have an acute angle. So we're given that A is 50 degrees. So 50 is not special. So we're not going to get a nice form for anything with sine of 50 degrees. B is 10, and A is 8. So this side is 10, this side is 8, and A is 50 degrees. And that's triangle is roughly drawn to scale in that case. All right. Use the law of sines to find B. That's the plan. And then once you find B, now I've got two angles. Use the fact that they all add up to 180 degrees to find the third angle, C. Now we've got all three angles and we've got one of the sides. Actually, we've got two of the sides. So we just use the law of sines one more time to get the third side, and then we're done. So let's try this. So you remember the SSA case from high school? Do you remember anything peculiar about it? You didn't care for it?
You have to be careful.
Oh, you had to be careful, yeah. The SSA actually doesn't uniquely determine the triangle. If you know SSA, there might actually be two distinct triangles that have the same SSA values. We're going to see that, how that comes out in the wash here. All right. So use the law of sines to find D. So what do? I use this. I know what A is. I know what little b is. I know what sine of big A is. I need to find sine of big B. So I solve for sine of B. Sine of B is B over A times sine of A. And that gives me about a 0.95756 using the calculator because A is not a special angle. It's just 50 degrees. Okay? So how do I find B? I know that sine of B is equal to that. So how do I find B? I do the inverse sine. So I go take the arc sine of this, and that gives you an angle B, whose sine is this. And for that, I get 73.25 degrees. All right. So in this case, B is 73.25 degrees, and looks about right. Okay. So now, what do? Well, this is not the only solution. That's the point. This equation, sine of b is equal to that. So unit circle time. So y is 0.9576. That you always will, except for the case where it's y is equal to 1. If y is anything less than 1, you will always get two solutions here. Those you'll get supplementary solutions. Now, when you use the sine inverse, which solution are you getting? You're getting the acute solution, the one in quadrant 1, because the sine arcsine will always give you something in that half. So it will give you that one, it will not give you that one. So here's the point. When you use the law of sines to find an angle from its sine, keep in mind that you will generally get two solutions. You will get an acute solution, and you'll get its supplement, which is 180 degrees minus that. And that corresponds to this. See, you've got the same angle A, same B, same A, same little a, but you can sort of swivel this over to there, and you get a different angle for B. And in fact, the red angle is the supplement of the blue angle. It's 180 degrees minus. So you actually get two different triangles. You get two different solutions. And you know this because keep in mind that this is only going to give you one of the two solutions when you take the sine inverse. There's always the supplement. Okay. So the point is, B does not have to be acute. So this solution is not unique. There are two solutions that work. Now, I might give you more information about this. I might tell you that I might just tell you that B is acute, or that B. What if B is not acute and it's not 90 degrees? What's it called? Obtuse. Right. So I might tell you that B is obtuse, in which case you would have to take the supplement of what you got from the arcsine. So you get that, and so the supplement is 106.75 roughly. All right, so to make a long story short, let's compute C in both cases. So what's C going to be?
It's going to be like
so if B is
6.75.
Yeah, if B is acute, you're going to get 180 minus 50, which is 130 minus B. So 130 minus 73.25, okay, that's whatever it is. If B is equal to this, then you're going to get 130 minus that. Both of those give you positive angles. Okay? Then you go ahead and you use the law of sines to find little c. And then you're done. So do this in 3 steps. Compute the sine inverse to find angle B and take that or its supplement as a possible solution. And then find the third angle, C, and then use the law of sines to find its opposite side, little c. Yeah.
If this was a SSA where they gave us big A, little b, little c, would it still have 2 solutions potentially?
Say that again. If they give you big A, little b, and little c, that's SAS.
Oh, okay.
So that's that actually does have a unique solution.
If they gave big C instead of big A, then.
Oh, big C, little b, little c. Yeah, that's SSA. That's the same thing. It's just rotated around.
So, okay, you have to have the side opposite the angle they give you in the what we're given.
Right.
Okay.
Right. The thing is, there's no. If you want, you can always relabel the vertices and the sides. You can rotate, you can permute the letters any way you want to if you prefer that you always know what angle A is, say. You always start with angle A. There's no reason you have to start with angle C. Okay? So here's where you get two solutions. So here you get two angles for C, and they both work. You get the blue angle, which is bigger than the red angle. Okay, so all of that. So 56.75. For the value of C, that will give you 8.73. That's the blue. Or if you use this solution for B, you get a much smaller angle for C, the red angle, which is 23.25. Plug that in for little c, and you only get 4.12. That's the red line. So the blue solution gives you a much longer c than the red solution does, which is only 4.12. Okay. All right. So it actually, there's some more stuff to say about this case. But here's the general procedure. Use the law of sines to find the angle B. And if you have to relabel your vertices so that you know what A is, know what angle, big angle A, little side B, and little side A is, just do that. Use the law of sines to find B. This will generally give you two solutions. Plug those in to get two possible values for C. And then use the law of sines to find little c in each of those two cases. And if you have extra information, like you know that I tell you that B is acute or B is obtuse, then you can just ignore one of the two solutions for B. Okay. So here's some more SSA case. You might not get any solutions for B. Let's see how that can happen. So instead of A, so same angle, 50 degrees, B is still 10, but instead of A being 8, we're going to change it to 7. Okay. So now we solve for sine of B, and instead of getting 0.9576, we get 1.09 something. What happens when you put that in your calculator? What's going to happen? You're going to get an error because this is not in the domain of sine inverse. You have to have a number between -1 and 1. So that's not in the domain. So there are no solutions for this. So there is no triangle that has this angle, that side for B, and the opposite side being 7. So there are no solutions, and the reason is A is too short. This number is small, so it boosted this whole number bigger than 1. A, the shortest that A could possibly be is the length of the perpendicular down to the horizontal line. That's the shortest A could be. But in this case, A is actually shorter than that. And you could find out what this length is, because this length, you just have a right triangle now. And you know that that's 50 and that's 10. So the sine of A is the length h of c divided by b. So h of c is b times sine of A. So if A is less than that, that's about 7.66. So if A is 8, it works. If A is less than this, if it's 7, it doesn't work. If it's less than that. Whoops. So the thing is, A is too short. So if you swing it around C, it's never going to hit the base. All right. Let's do something else. Now let's change A, make it really big. Let's change it to 12. So if we change it to 12, then this is going to make this big, And now this is going to be, so this is going to be smaller. It's only going to be 0.6384. Okay. So then I get two solutions for B, right? So now I get two solutions. But now I'm in this situation. A is longer than B. So do I actually get two triangles this way? No, I only get one, because if I swing this around, it's going to go on the wrong side. It's going to miss the base. So I only get one triangle this way, and this is when B is acute. Suppose I didn't know that, and I just was blindly applying the procedure. How would I find that out?
Sometimes you get a negative value.
Yeah, so when you go to find the third angle C, one of the values you get will be negative. All the angles will be positive in a triangle. So the thing is, that doesn't work because that effectively gives you a negative angle for C. So you will know this when you go and you find out, when you compute the third angle C, you're going to take 180 degrees minus A minus B. If you take the obtuse solution for B, you get a negative C, so you know you can ignore that and just take the acute solution for B. Oops. All right. So that's really the situation. There's nothing here that says A has to be acute. A could be obtuse. And, you really don't have to digest this. This is really just going over all the cases that you can have where you have and the number of solutions that you get. But that's not really necessary because if you just blindly apply the recipe, use the law of sines to find B, take two solutions, and then find the third angle C, just throw out any solutions that don't make sense. So if C is negative, that's not a solution. Just throw that out. And so you don't have to know this because you'll just find it out as you go. So there's no reason to know this. So here's A is obtuse. In this case, if A is obtuse, then in fact you will always only get one solution, and it's the acute solution for B. So as a shortcut, if you know that A is obtuse, then you can just take the acute solution, take the arc sine of the number, and you know that that's going to be the only solution. Because there's no obtuse solution. Okay. All right. That's all I want to say about ASS. Okay. So more of that stuff that you don't have to know. Okay. So what is the area of the triangle? The area of the triangle is 1/2 base times height. That's the standard formula. Well, in terms of trig function, we can find that out. So if the base is C, little c, what's the height? Well, you can write that in, for example, the height divided by A is, that's like the opposite divided by the hypotenuse of B. So that's the sine of B. So sine of B is B divided, is the height divided by A. So, to take the area, you take 1/2 the base, that's C, times this height, which is A times the sine of B. And that gives you a formula for the area of the triangle, just in terms of the sides and the sine of one of the angles. There's no reason you have to choose B as your angle. You can permute, you can relabel things, and you get 3 separate formulas for the area. And I'm not going to do the example. I'm just going to gloss over this. Blah-de-blah-de-blah. You can use the law of sines to find the other two. But basically, the area is take 1/2, the product of 2 of the 3 sides, and then the sine of the angle included between them. And that will always give you the area. that's kind of hard to see. So we get three separate formulas for this. 1/2 BC sine A, or 1/2 AC sine B, or 1/2 AB sine C. Just leave it at that. Don't need an example because we could just plug the numbers in. I'll go on to more stuff. Law of cosine. So there are some cases that law of sines alone does not handle. And we need a second law, and this is called the law of cosines. So, start with a right triangle. So suppose C is 90 degrees. Then Pythagorean theorem says that C squared is A squared plus B squared. The law of cosine, all that is just, C doesn't have to be 90 degrees. So what you get instead of the Pythagorean theorem, you get this correction term that you have to add in. Now, if C is 90 degrees, then cosine of C is 0, so that term goes away, and you're just left with Pythagorean theorem. But so the law of cosines really is sort of a generalization of the Pythagorean theorem, where the angle here doesn't have to be a right angle; it could be any angle. And then you just add this correction term in. Okay, so that's the law of cosine. Notice that if C, all right, so C is 0 to 90. If C is less than 90, then this is positive, and so C squared is going to be less than A squared plus B squared. And that kind of makes sense. If C is acute, then the hypotenuse is going to be less than it would otherwise be. A and B still being equal. And if C is obtuse, then that term is positive, and the hypotenuse is longer than it would otherwise be. So C squared is bigger than A squared plus B squared. Okay. This is the standard form of the law of cosines. So here's what it's used for. If you know A and B and the angle C, then you can find the opposite side of C. There are alternate forms, and the alternate forms you get by solving for cosine of the angle, cosine of C. So cosine of C, if I solve for cosine of C, I'm going to get A squared plus B squared minus C squared all divided by 2AB. So take that equation, solve for cosine of C. That is an alternate, it's called one of the alternative forms of the law of cosine. So that's the standard form. This is an alternate form. You can always get one from the other. When would you use the alternate form? Yeah, when you know all three sides, but you don't know any angles. So use the alternate form when you know all three sides, and you want to get one of the angles. Okay. So there's nothing special about picking C here, right? You can just freely relabel these vertices and get other alternate forms. So you could get cosine of A is equal to that, cosine of B is equal to that. There's the standard form, there's the alternate form in terms of cosine of A, and here's the standard form and alternate form in terms of cosine of B. Okay. In the standard form, the angle is always the same letter as the other side. It's the opposite side. All right. So when to use the law of cosine? So you got to use the law of cosine in the two other cases that we haven't looked at yet, which are SSS and SAS. So in SSS and SAS, there's always going to be one unique solution. So here's what to do in SSS. Find any two angles using the law of cosines, alternate form. So do that twice to find one angle and then find another angle, okay? And then find the third angle using the usual that they add up to pi. Okay, so that's what you can do in SSS. In SAS, you find, so SAS is when you've got this. You've got the angle, and you've got this side, or say B and C, and you've got A. So you've got all that. And that's SAS. So first, you find the opposite side using the standard form of law of cosine. I'm sorry, this is A. So A squared is B squared plus C squared minus 2BC cosine A. That's the standard form. Now, once you have the third side, you could proceed like you did in SSS and find another angle using the law of cosine's alternate form, for example. Or, yeah, so right, that's what I said. And then find the third angle using ABC, A plus B plus C plus Y. All right, so let's do an example of SSS. And then we pretty much know all the techniques we need to know for solving triangles. So, in SSS, I've got three sides. A equals 2, B equals 3, C equals 4. Use the law of cosine's alternate form to find cosine of A. So plug in the numbers B squared plus C squared minus A squared over 2BC, and I get 7/8. So what does that tell you A is? It's the cosine, arc cosine of 7/8. Okay? And get 28.955. Here's the nice thing. There's nothing to worry about here. There's no caveats. Just always works. Okay? There's never a chance for a second solution. The fact is, the cosine inverse function, the domain, well, the point is, the range of the arc cosine are the angles from 0 to 180. Those are exactly the angles, possible angles in a triangle. So whatever this gives you, that is the angle. And there is only one solution to this in the range 0 to 180. So that's it. So you get 28.955 degrees. That tells you what A is. Now you can find B, again, using the law of cosine's alternate form. Plug in B is now, cosine of B is A squared plus C squared minus B squared over 2AC. And that gives you 11/16. So B is the cosine inverse of that, which is 46.567. And now you find C, 180 degrees minus these two, and it's 104. So you're given three sides, and you've got to find the three angles. Find two of them using the law of cosines, and then the third one using this. All right. There's another approach you could use for that. Am I going to do an SAS? I want to do an SAS. Well, all right. I'll do, maybe if I don't have an SAS on the slides, I'll do it on the board. So there's another approach to SSS and SAS. Oh, there is?
2 slides from now.
2 slides from now? Good. Thanks. All right. So in SSS, you always use the law of cosines first to find the largest angle. But now you find the largest angle. Okay? And the reason is because there's going to be a caveat. So cosine of C is all of that. And that gives you a minus 1/4. So C is inverse cosine of minus 1/4. Well, if x is in minus territory, the result is going to be obtuse. Okay. This is the largest angle. It has to be. How do you know what angle is the largest angle?
Longer side.
Yes. So the rule about triangle is as follows, and it's almost worth writing down. The largest angle is opposite the largest side. And the smallest angle is opposite the smallest side. And the angle in the middle is opposite the side that's in the middle, between the largest and the smallest. Okay. So the ranking of the angles is the same as the ranking of the opposite sides. Okay. The other property of a triangle is that no triangle, every triangle can have only one obtuse angle. It can never have two obtuse angles, because if you have two obtuse angles, they add up to more than 180. So every triangle can only have at most one obtuse angle, and that's going to be the largest. So here's why you want to find the largest this way, because you know the law of cosines is completely safe. You take the cosine inverse of this thing, and it gives you the largest angle. Then that allows you to use the law of sines to find another angle, because the other two angles have to be acute. So when you use the law of sines, and you use the law of sines, you find the angle from its sine, you know it's acute already. If you didn't know it was acute, if you tried to do this with a largest angle, and you accidentally picked the acute version when it was really obtuse, you could really screw yourself up, and you wouldn't know that you messed yourself up easily. You would get the wrong answer, and there wouldn't be any easy sanity check to tell you that you got the wrong answer. So in this case, you can use the law of sines after you use the law of cosines, because the law of sines is easier to work with. It's less calculation. That's why you might want to use it instead. But the caveat is only use the law of sines in a case like SSS or SAS. Only use the law of sines if you know that the angle is acute. And you can tell that it's acute if it's not the largest. So maybe in SAS, maybe you know one of the angles and it's acute. So in SAS, maybe B is equal to 10 and C is equal to 8, and this is acute. So you can use the law of sines to find one of the two angles. Which angle should you use the law of sines for?
C.
C. Why C?
You know it's not the largest.
Right, because you know it's not the largest. Because it's opposite a side that's 8, and there's a longer side, 10. So you know that B is larger than C, so C cannot be obtuse. It has to be acute. So when you find C using the law of sines, just hit the arc sign button, and that will give you the correct answer. All right. So that's the only caveat. If you use the law of sines to find an angle in SSS or SAS, just make sure it's not the largest, and so there's no danger of picking the wrong solution. Okay. So for example, well, here in SSS, we made it safe to proceed because we know what the largest angle is. It's going to be C, because it's opposite the largest side. So we just went ahead and found angle C from its cosine, and that always works. There's never any worry about a second solution there. That'll always give you the right answer. And so now we know the other two have to be acute. So, for example, sine of A is A sine big C over little c. So plugging in everything we know, that's 2 sine 1/48 over 4. That's about 4.4841. So A, sine inverse of that. Now, I said, there's the second solution here, but this is the one that's correct. So take this and not the supplement, because we know that A is acute because it's not the largest angle. Okay. the rest of the animation says that in a nutshell. So 28.95 is the unique solution for A. And then you find B finally by doing the usual thing, and you get 46.5. Questions? All right. Let's do an SAS case. So we find the missing side and angles, given that A is 30, B is 3, and C is 5. So let's draw that in. So that's C, that's B, that's A, and that's 30 degrees. And B is equal to 3, and C is equal to 5, and that's little a. So we have those three things. So at this point, there's only one thing we can do to start out. We have to find little a using the standard law of cosines, which says that a squared is b squared plus c squared minus 2bc cosine a. We know everything on the right. So we plug it in, and that is a special angle, and it turns out to be root 3 over 2. So this simplifies to 34 minus 15 root 3, and that's a squared. Don't forget to take the square root when you find a. So it's the square root of all of that. And is it plus or is it minus? It's always plus because all of these sides are going to have positive length. Unsigned quantity. So a is the square root of all of this, and it's approximately 2.832. So let's write that in. Approximately 2.832. Remember what I said a couple days ago about compounding round-off error in your calculator? So the thing not to do is just to write down a few decimal places on a piece of paper and then type it in later. Try as hard as you can to store this somewhere in your calculator using your calculator's full precision. So the most precision available in your calculator, because we're going to take this and use it in further calculations. So you don't want to compound the round-off error more than you have to. So now we can use the law of sines. Yeah, you can always use the law of cosine and not worry about which angle is smaller. But which angle is smaller, B or C? B. So if you just know that, use the law of sines because it's a little bit simpler. So law of sines says find the smaller angle B. So sine of B of B. Solve for sine of B. You get this. We know everything there. Plug it all in, and we get 0.5297. Okay, using our A that we got previously. So there are two solutions. One is a supplement to the other. One's going to be acute and the other's obtuse. But we know that B, because it's a smaller, it's not the largest angle in the triangle, so it has to be acute. So we only take the acute solution. Okay. So B really is the sine inverse, the arc sine of 0.5297. And we get a nice acute angle, 31.97. Plug that in here. 31.97 degrees. And then finally we get C by taking 180 degrees and subtracting A and B. This is 118.03 degrees. That solves it. All right. Questions on SAS? All right. SSS, what if you want to find the area in SSS? So this is our last topic, and so this won't take 5 minutes.
If I'm one side.
Sorry, what?
You just have to find one side. I mean, one angle.
Yeah, okay, so you could find one angle, and then once you have one angle, then you have the angle, and you've got the two sides adjacent to it. Plug that in. Okay? And that'll work just fine. So how do you get that one angle? Use the law of cosine. So here's the interesting thing. You use the law of cosine. Suppose, all right, so these are concrete numbers, and we plug them in, and we get minus 1/2 for cosine of A. So from cosine of A, we have to find sine of A. A is between 0 and 180 degrees, so the sine of A is going to be positive always. So we can use the Pythagorean identity and take the positive square root of 1 minus cosine squared of A. Okay, and it's not plus or minus because we know that sine in A is positive. So we do all of that and we get square root of 3/4. Great, that's sine of A. Now we take that and multiply it by what? Multiply it by B and C, which are adjacent to it. So 3 times 5 times that times 1/2. And that gives you the area. So plugging that all in, simplifying 15√3/4. So you can find the area that way. This is actually exact. All right. So lastly, there's a shortcut to this. And the shortcut is basically do this for all possible A, B, and C. Just call this A, B, and C, and run through this whole formula just using A, B, and C, and solve for this. Now instead of concrete numbers in here, I actually have letters. I actually have variables. And simplify, you get a really nice formula that gives you the area of the triangle just in terms of the sides A, B, and C. You don't have to find an angle or its sine or its cosine. And basically you just go back and do this in general and you make the substitutions, and if you do this and you simplify everything like you did, then you get what's called Heron's formula. This was known since ancient times. And it's as follows. The area of a triangle, if you know the 3 sides of the triangle, here's how you get the area. It's very simple. First, you compute the half of the angle of the triangle's perimeter. So S is the perimeter of the triangle. A plus B plus B divided by 2. This is sometimes called the semi-perimeter. So S is the semi-perimeter. Then what you do is just take S, then S minus A, S minus B, S minus C, multiply those 4 terms together, take the square root, that's your area. So this is Heron's formula for area. Anyone not know Heron's formula until now? Yeah, a couple of people. All right. So there was learning taking place just now. Okay. So let's do this for the triangle in question. So 7 plus 3 plus 5 is 15. Divided by 2 is 15/2, so that's S. Now I got to find these other things. S minus A is 1/2. S minus B is 9/2. S minus C is 5/2. Plug that all in, I get 15/2 times 1/2 times 9/2. So 5/2. That's 3 times 9 times 25. 15 is 3 times 5. So I'm actually combining the 2 5s together to get 25 because that's a perfect square, and I can pull that out. And then 9 is another perfect square, and then I have a 3 left over, and then I'll divide by 16, which is 4 2s. Square root of 16 is 4, and from the square root I can pull out square root of 9 is 3, and the square root of 25 is 5, and I'm left just with the square root of 3 inside. So that gives me 15/3/4, what we got before. Okay, so this is Heron's formula. And it's nice because it's symmetric. It treats A, B, and C kind of on an equal footing. It doesn't prefer finding one of the angles. It just sort of works regardless. Any questions on anything? I think that's it. I think I'm done. Yeah, I'm done. Right on time. Okay. So, all right. That's it. That's all I got.